degree C, and the outer surface will have a boundary condition of convection. K dt dr is equal to H. This must be T wall minus T ambient because it's reject to ambient. So this is the first boundary condition. This is a second boundary condition. So next what we are going to do is to solve this cylindrical coordinate. So we are going to use cylindrical coordinate, not Cartesian coordinate, because the area is not the same. So integrate this twice, what you're going to get is TR is equal to C1 ln R plus C2. Okay, so the first boundary condition is so the radius is 4.25. C1 ln 4.25 equal C2 equal, oh, not equal to C2, plus C2. This is going to be equal to 95. To solve this, you can get the value. Not get the value, you're going to get a constant. Okay, so you're going to get constant 95 is equal to 1.44 C1 plus C2. So next, you are going to solve for second boundary condition. For second boundary condition, so you have second. Okay, for second boundary condition, you need to solve this one. So from dt dr is basically, if you solve this, you're going to get dt dr equal to C1 divided by R. But since we are working at R2, so dt dr at R2 equal to C1 over R2. So you replace this inside here, you're going to get a K C1 R2 equal to H T minus T ambient. Alright, so this T represent the T at outer wall. You're going to use this equation to get the value of, to get a function of T at outer wall. So T 4.75 is equal to C1 ln 4.75 plus C2. And then you replace this part into here. Okay. With K value of air of 0.029, more or less. So you are going to have a function. So with 6.238, C1 plus 4 C2 equal to 80. So you have a A and you have a B equation. So you have two equations with two unknown. You can use your calculator to solve this you can solve these two equation A and B to get, with the aim to get C1 and C2. Two equation, two unknown is solvable in your directly in your calculator. So your C1 will be minus 627.61 and your C2 will be 998.76. So finally, your specific equation for this problem is minus 627.61 ln R plus 998.72. Okay, so you can plug in any R value to get any point of temperature. For example, if you want the surface temperature, the outer surface temperature. So you don't know the outer surface temperature. What you have is boundary condition, and this boundary condition in the form of differential. Therefore, you don't know the specific temperature, unlike the internal part. So the internal part, because it's a fixed temperature 95. But if you want to know the external part of the outer surface of the flask, so you put this R replace bit 4.75, you can get the answer of the outer surface. So next we are going to calculate the heat transfer rate. So general equation is Q is equal to minus K A dt dr. So you can use this equation, okay, to calculate the heat transfer rate. Okay, for this one, it's quite straightforward. So you have two body condition on the left. So this is a bit tricky. You have a fixed temperature and you have a heat flux K dt over dx. So you can apply this two boundary condition in this equation in cylindrical Cartesian coordinate, and then you can get your answer. But since one is in differential and one is in fixed temperature, so basically you can get your C1 and C2. So what you need is at least two conditions to determine C1 and C2. Alright, so next we move on to the next topic, basically thermal resistor network. So the previous topic will cover one question in your test 1.